Hey guys, sorry I cannot be here today. I'm in an articulation meeting with the middle school teachers, but I'm glad that you're here, and you have a lesson in Chapter 7, Section 1 on exponential growth and decay. We're going to look at equations, applications, and in particular, most importantly, we're going to look at the parent graph for exponential growth and decay today. These notes will be online, and the video will be on, well, obviously you're watching it, so it's already on YouTube. So if you need to go back and take a look at this, you can. Exponential growth and decay functions are a little bit different than what we've been working with. We have growth from left to right. We're talking about something that increases. That's how you know this graph is increasing, the first one. And then left to right on the second graph, this one decreases. So here, as we go from left to right, the graph goes up. That's growth. And from left to right, this graph gets smaller. That's decay. Your function for growth and decay applications looks like this. Y equals AB to the x power. Notice this is the first time where we're dealing with an equation with your variable is in the power position. That's not very typical for us. Y is your ending amount. A is your starting amount. B is called your growth factor. And we'll talk a little bit more about the growth factor because that's going to determine whether it's literally growth or decay. And X is the number of growth periods. Please be careful with X. This is not time. It's the number of growth periods within a certain amount of time. So don't confuse X with time on these applications. So Y equals AB to the X. B, your growth factor. If B is greater than 1, then we find B by doing 1 plus the percent increase. Right here is your equation. B is 1 plus the percent increase. That's when you get exponential growth, when B is greater than 1. So if you have a growth of 6.8% per year, then we're going to add the decimal value of 6.8%, 0.068, to the 1. And you're going to get a B value, a growth factor of 1.068. Since that is greater than 1, if you were to graph this, your graph would increase from left to right. The key to this is when B is greater than 1, you have growth. Exponential growth, B has to be greater than 1. That's your key. Let's take a look at the graph now. Y equals AB to the x. And we're going to look at this function in general, and then we're going to go back to the parent graph and talk specifically. So I threw 4 functions up here. Y equals 2 to the x, y equals 3 to the x, y equals 4 to the x, and y equals 8 to the x. I'd like you to take 30 seconds right now and see if you can sketch the graph for any one of these. And the input values that we're suggesting you use are for x, -1, 0, and 1. So pick any one of these graphs and see if you can figure out what the graph would look like for -1, x, and 0 for x, and 1 for x. What would the graph look like? So just take a minute to do that. Now think about why did I tell you to use -1, 0, and 1? Think about that question. We're going to come back to the answer to that in a minute. So let's look at y equals 2 to the x. Well, let's look at y equals 3 to the x first and see if this one will work for us. So if we connect that here, that's what y equals 3 to the x looks like. Notice the points that it's going through. It's going through the point -1, 1/3. -1, 1/3 right here. 0, 1, and 1, 3. Okay. It doesn't want to let me graph y equals 2 to the x, so I'll do that freehand for you. That graph is going to go through, we'll do it in green, it's going to go through -1/2, 0, 1, and 1, 2. So that graph is going to go like this in green. Very similar to the one in red. If we do y equals 4 to the x, I'll graph that one over here. Notice that goes through the point -1, 1/4, 0, 1, and 1, 4. And if we put y equals 8 to the x on the same graph as that, theoretically it will graph it, but maybe it just doesn't want to work today. Nothing's working today. Okay, so we're not going to get that one graphed either. That's going to go through the points 1/8, -1, 1/8. Still going to go through 0, 1, and then it's going to go through the point 1/8. So again, it's going to hug along here, a little bit lower, come through, and a little bit steeper than this other graph. Y equals 4 to the x. So there's a great question here. It's a great question here. Every graph passes through, and it says, what points is it going to pass through? Every graph is going to pass through what point? So if we go back and we look at those graphs, obviously I'm losing one of them. Here's the graph on the left here. Every graph is going to go through what points? What points? Give me one of those points. Chase, give me a point. So one of the points was 0, 1. That's the most obvious that they all go through. Now the other points aren't quite as obvious. But if you look at the points, you're going to see that these points here are right one up, and then whatever the number is that's being raised to a power. So 1, comma, whatever your base is. And then -1, 1 over whatever the base was. Those values are going to become important for us when we're graphing. Now the book refers to this form y equals a times b raised to the x minus h power plus k, and that's a lot like our translational form using a's, b's, and c's. And really, the h and the k is your imaginary starting point. It's your translation vector. In A, what does the A represent? What's the A represent, Jen? Come on, you should know that. That's right, A is the vertical stretch factor. So that's always going to be your vertical stretch factor. And B, technically, is your growth factor. Okay, this might be kind of confusing. Mr. Stedman is using this 1 comma A times B from your imaginary starting point. We're going to look at it more like this. Every parent graph that is exponential, y equals b to the power of x, we don't really care what b is. Every single one that's, regardless of what b is, will always go right one up one, excuse me, right one up b, right 0 up 1, and left 1 up 1 over b. Right 1 up b, right 0 up 1, and left 1 up 1 over b. So if you look at them as coordinates on the left-hand side here, you can look at these as the coordinate pairs, 1 comma b, 0, 1, and negative 1, 1 over b. Notice that this is the first time this has happened for us. The most important point on our graph, the origin, is not on the graph itself. It's still an important point, and it's where we start everything from, but it is not a point on the graph. And no matter what b is, no matter what the value for b is, as long as b is greater than 0, and b by definition has to be greater than 0, we can never get a negative value for y. So on the left-hand side of our graph, we approach the x-axis here, but we never get there. What's this pink dotted line called right here? What do we call the dotted line? That's right, this is an asymptote. And since it's horizontal, we're going to call it a horizontal asymptote. And the equation is always going to be y equals 0. So the equation for the horizontal asymptote in the parent graph, y equals b to the x, is y equals 0. So we're going to approach that asymptote, but never get there. So make sure on your graphs, as you get closer to the asymptote, the graph kind of pushes that asymptote. The critical movements again, right 1 up b, right 0 up 1, left 1 up 1 over b. This is the one you want to memorize. And this doesn't matter whether b is greater than 1 or between 0 and 1. If it's greater than 1, this is your graph. It's a takeoff. If b is less than 1, I'll show you what it would look like, even though we're not going to focus on it right now. But it would come down, and it would be like a plane landing. It would get closer and closer and closer to that asymptote. Okay. Right now, we don't want to think about b being between 0 and 1. We just want to look at the b being greater than 1, so our graph is a takeoff. So if you have something like y equals 2 to the x, we make our list. Nelson, what's the parent graph? It's not y equals b to the x. We want to be very specific. So in this case, it's going to be y equals literally, right, 2 to the x. There's no translating, and there's no vertical stretch. It's just be considered a 1. The horizontal asymptote, important to get used to adding that to our list for exponentials, going to be y equals 0. This is a parent graph, so we don't really need anything in the list except y equals 2 to the x. It's a parent graph. So when we're graphing y equals 2 to the x, it goes right 1 up 2. Right 0 up 1, and left 1 up 1 over 2 in this case. That's enough to do the graph, but you should know that if you went right 2 in this case, you'd go up 4, and that's still on the graph, so it's worth putting that point on there. So when we start, we hug the asymptote, we come through our points, and we head to take off. There's your parent graph. Y equals 5 to the x, also a parent graph. So nothing mysterious here, no translating, no vertical stretch, and horizontal asymptote again is at y equals 0. Your critical points always goes through 0, 1, right 0, up 1, right 1, up whatever your base is. Your base is 5. And left 1, up 1 over the base. Notice as our base gets bigger, 2, 3, 4, 5 in this case, the graph gets steeper. So we come along the x-axis, go through our critical points, and that's our graph. Make sure you have zeros on the ends. Remember, it's right 1, up b. In this case, your base is 5. So it's right 1, up 5. Right 0, up 1 always. And left 1, up 1 over 5. Since your base is 5, whatever your base is, you're plugging that in where you say b. So if we go back to our Rosetta Stone idea of how to graph, and again we're ignoring the fact that we could have a horizontal stretch factor, that's going to come in this chapter, but it's not here today. So if we look for AB, capital A, capital B isn't there because there's no horizontal stretching, C and D. If we did have a capital B, it would go in front of this parentheses in the power position. But I don't want to confuse you with that. It's going to come, it's just not coming today. Okay? This lowercase b is your base for your function. So whatever that base is to the power of x, that's your parent graph. Translation vector is still c comma d. Vertical stretch factor is still a. And the add for us, what's important here, your horizontal asymptote is going to be y is equal to whatever the d value is of your translation vector. That's where your asymptote goes. And we'll take a look at how that works for us. But this y equals d is all based on your translation vector. So we have a, b, c, and d, except we have no capital B still. So when we look at a graph that's not a parent graph, y equals 4 to the x, that's a parent graph. We don't need to do that. Let's look at the one over here, number 2, where the parent graph is y equals 3 to the power of x. There's no translating. No translating going on here. Irene, what's the vertical stretch factor? Good. That's what I got too. Now, this is the tricky part because we haven't had to deal with this before. What is the horizontal asymptote? It's got to be written as an equation. Remember, it's a horizontal line. So if it's a horizontal line, it's got to be y equals. What's it going to equal, Cole? Right, it's the y coordinate of your horizontal asymptote. Sorry, your translation vector. The horizontal asymptote is the y coordinate of your translation vector. So if we're going to graph this, we start with our translation vector, which is 0, 0, so that's where our origin is. Right through our new origin, we draw a horizontal asymptote. We have a vertical stretch factor. That means anything after the word up, we multiply by the vertical stretch factor. So, right 1, we should be going up 3. We're going to go right 1, up 1.5. Right 0, up 1 becomes right 0, up 0.5. And left 1, up 1 over 3 becomes left 1, up 1 over 6. Now, sometimes that's not enough, especially when you have a vertical stretch factor less than 1. It's hard to get the whole graph in there. I would usually go right 2 here, and instead of going up 9, we're going to go right 2, up 4.5. That point is a legitimate point on our graph. We're not going to be able to go right 3, up 27 divided by 2, because that's off of our graph, so that's enough. Make sure that when you get to the top of this grid that you're crossing through right here before you get to the x equals 3 value. And that's what your graph should look like. Okay? So maybe we can connect these two. And you can see it's in the same spot. Now what about your domain for this? What about your domain? What can't x be? X can be anything. So how do we say x can be anything? That's all reals. So we're going to go from negative infinity to infinity. What about your range? Your y values are going to start at your asymptote, your horizontal asymptote, and go up. Your horizontal asymptote here starts at y equals 0, so it's going to start at 0 and go up. So for our purposes, it can't be equal to 0 because that's an asymptote, and we're going to go to positive infinity, so it's going to look like that. Domain is all reals. For exponentials, it's always all reals. Domain is always all reals. And then your range is going to be restricted based on where your asymptote is. If you look at this one, we have y equals 3 times x plus 1 in the exponent position plus 2. Kate, what's the parent graph? Sorry? Y equals 3 to the x. Okay? Y equals 3 to the x. Kirk, what is the translation vector? Negative 1, 2. Very good. How about the vertical stretch factor, Aaron? There is no vertical stretch factor. Good. So you could put a 1 and just leave it blank. It doesn't really matter to me. 3 is not the vertical stretch factor. 3 is your base. So once you have those filled in, you ought to be able to come up with the horizontal asymptote. But remember, the horizontal asymptote is always an equation. It starts with y equals, Michaelin, y equals, and it's whatever the y coordinate of your translation vector is. So in this case, it's going to be very good, too. Now you can always do the domain right now. The domain is easy. It's always negative infinity to infinity. It's always all reals. There's no mystery to that. The range is always a little bit tricky. So what I usually do is I look at my graph. So at negative 1, 2, there's my new origin. Not a point on the graph, it's just the new origin. There's my asymptote. It goes right through the new origin. Now, all I have to do is count boxes. Right 1, up 3. Right 0, up 1. Left 1, up a third. That's all you need. Then we push the asymptote on the left. Like that. Once you have the graph, it's pretty easy to see. Your asymptote goes from there, the graph goes up. So that means we start with the y value, which is equal to our asymptote, which is 2. And we're going to go to positive infinity. And we can't get to the 2, so don't hug the 2 on these. Shun the 2, shun the infinity. You can never get to infinity. Let's look at one that has a flip and a stretch factor. If it has a flip, it's got to have a stretch factor. Same parent graph that we just dealt with, y equals 3 to the x. Tyler, what's the translation vector? Negative 1, 2. Now, in this case, we're going to have a vertical stretch factor. Dayton, what's the vertical stretch factor? Good, negative 2. The horizontal asymptote is always going to be easy to find. Grant, what is it? Remember, if you don't see it, it's always the y coordinate of your translation vector. So in this case, y equals 2. So the first thing we want to do is move our origin, left 1, up 2. if you want, you can do your domain, because the domain for exponentials, always all reals. Negative infinity to positive infinity. Be careful on the range this time. You might want to graph it first. So if I throw the graph on here, we're going to be, normally it's right 1, up 3. We're going to go right 1, down 6. Normally from the new origin, it's right 0, up 1. We're going to go right 0, down 2. And normally left 1, up 1 over 3. We're going to go left 1, down 2 over 3. So that graph is going to come off the asymptote from below and hit these points to get a flipped version of your exponential graph, which means that your range restriction is going to come from negative infinity, that's the small side, we're going up, and we're going to get to the 2 value, but we're never going to quite reach 2. It's asymptotic. We're going to approach, but not get to. So this graph is a little bit tricky because of the negative 2. Otherwise, it's not very different than what we did right here. 3 to the power of x plus 1 plus 2, 3 to the power of x plus 1 plus 2, but we have a negative 2 vertical stretch, which causes a flip. So this one has a base of 3 over 2. That means that's your parent graph. 3 over 2 to the power of x. The translation vector, nothing's being done with the x, so it's 0, and then after the function is the negative 2. We have no vertical stretch factor, and your horizontal asymptote. Again, if you can find the translation vector, you can always tell me what the horizontal asymptote is going to be. Jason, what's the horizontal asymptote? Y equals, right, negative 2. Alicia, what is the domain going to be? You can either say all reals, or right, negative infinity to positive infinity, all reals. The domain is always all reals. Now remember, your base is a fraction, so you've got to be a little bit careful with how you graph it. It's still more than 1, so you're still looking at growth. When we graph the points, right 1 up the base. Whoops. Let's put in our horizontal asymptote first. So 0, negative 2 is your translation vector. Horizontal asymptote is going to go right here. And from the new origin, we're going to go right 1, up 1.5. Right 0, always up 1, even when it's a fractional base. And left 1, up 1 over the base. That means take the reciprocal of 3 over 2, which is going to be 2 over 3. So 1 over 3 over 2 is equal to 2 over 3. We just take the reciprocal of the base. Now that doesn't look like enough points to know what the shape is going to do to the right. We know that on the left we're just going to come off the asymptote. We're going to get to here. Now you might want to throw in another point. If you go right 2, when you square the base, 3 over 2, you get 9 over 4. Right 2, up 2.25. Even then, we're still only right here. If you go right 3, you'd be 27 over 8. 27 over 8. If you reduce that or change it to a mixed number, 27 divided by 8 would be 3.5. Right? 3.5. 1, 2, 3 would be up to here. So at least you're getting some idea of what the shape is going to look like. And because of your base, that would be helpful. Your range starts at the negative 2 and goes to positive infinity on this one. But remember, it's shine on both sides of these because it's an asymptote. So you're seeing a variety of different types of exponential graphs, but as long as your base, whatever the number is right here, being raised to the power, is more than 1, all the graphs are takeoffs. The only exception to that was when we had a negative vertical stretch factor, which caused the graph to flip over. But that's just a reflection. Okay, so this one has everything. It has a stretch factor, it has a translation vector, and it has a base greater than 1. Parent graph is y equals 5 to the x. Translation vector, remember it's the opposite of what's with the x, so it's going to be a positive 3, negative 1, and your vertical stretch factor is 2. Your horizontal asymptote, y equals negative 1. You can see that's already put into place for us. If we start with the point 3, negative 1, we would be right here on the asymptote. Again, not a point on our graph. If we follow our parent graph movements, right 1 up b, right 0 up 1, and left 1 up 1 over b, we should be able to draw in this graph. Remember, your vertical stretch factor over here is 2. So right 1, normally we would go up 5. We're going to go right 1 up 10. So we'll be all the way up here. Normally it's right 0 up 1. We're going to go right 0 up 2. We're doubling the ups. And normally it's left 1 up 1 over 5. We're going to go left 1 up 2 over 5. And then we're going to come right along the asymptote and take off. Very steep. Very steep on this one. What's the domain? Domain is all reals. Never going to change that. So your domain, all values of x such that we go from negative infinity to infinity. Try to get used to using the set notation. For the range, all values of y such that we're going to start at negative 2 and go to positive infinity. Remember, don't include those. That's what we're looking for. Okay? So these are your parent graphs. It doesn't matter what your base is. It could be a 2, 3, 4, 5. It can be anything. This one's going to be a base 3. Okay? So let's take a look at your exponential growth. Remember I said earlier that b, your exponential growth, is 1 plus whatever your growth rate is. The percent increase is a good way to think about that. So what is b equal to? It's 1 plus whatever your growth factor is. So in this case, you look at this example, the computer is 1996, 2573 computer viruses, 2573. During the next 7 years, the number of incidents increased by 92% a year. Write an exponential growth model giving the number of incidents t years after 1996. Okay? About how many incidents were there in 2003. This one's brutal because they want you to use the graph to answer the questions. So if you look at the equation that they're asking you to do, if we have a 92% increase each year, what is the value of b? What is the value of b going to equal if b, again, is equal to 1 plus r? Remember, r's got to be a decimal. What would it be, Brennan? b equals exactly 1 plus 0.92 is 1.92. Does everybody see that? If b is 1.92, then you should be able to write the function at this point. So your function, if we use what they're asking you for, write an exponential growth model, the number of incidents n is going to equal 1.92 raised to the power of t, where t is time in years. So you can see we start off really small, 27 Sorry, we need that starting amount in here. N is equal to, what was it, 2573. So we start off at 0, 2573, and then we go up from there, and we're multiplying our ups by 1.92. Or we're multiplying our ups by 2573. Now I'm all confusing you. This graph, really difficult to show these numbers because the numbers get huge in a very short period of time. You're going to want to utilize your calculator to maybe determine some of these numbers. You notice at the bottom, I kind of labeled those numbers that you might plug in, years after 1996. So you might try plugging in a 1 year after 1996. You'd have 2573 times 1.92. So not a huge amount, not even 5,000 yet. But then, when you start going and putting in numbers like a 2, a 3, a 4, and a 5 for t, you can see that the numbers get quite a bit larger. And when you put in a 7 for t, you're going to get pretty close to 250,000. Don't beat yourself up with graphs like this because the accuracy becomes ridiculous when you start talking about 250,000 on a small piece of graph paper. This is a formula you're going to want to know, not like the computer one. A equals P times 1 plus R over N to the NT power. This is the formula we use for what's called compound interest. This is what happens at the bank, where you get interest on your interest. P is your principal. It's also your starting amount. A is your ending amount. R is your interest rate, and it's an annual interest rate. N is the number of compounding periods per year. So if I was compounding monthly, N would be 12. If you were compounding weekly, N would be 52. If you were doing it daily, N would be 365. And T is time in years. Now the reason why N is important is because you take your annual rate, R, and divide it by N. And that's very important for figuring out the rate for the growth period. So this formula is one you're going to want to add to your notes, and you're going to want to memorize it. So I'll give you a second to get that copied down before we change. I'll get you your test back to you tomorrow. Test scores were pretty good. We'll get them back tomorrow. You can see exactly how you ended up. Okay? Everyone get that? N is compounding periods per year, and T is time in years. So here's one that's done out both quarterly and daily for you. They are identical, except for the number of growth periods in a year. So if you take $4,000, that's your starting amount right here, times 1 plus R, your 2.92% annual interest, which is about triple probably what you're getting at a bank right now in your savings account. As a decimal, 0.0292. Compounding quarterly means 4 times a year. So every 3 months you get a statement. That's why we're putting in a 4 in for N in our formula. Remember up here, N is the number of times you're compounding per year. So in the example on the left, it's quarterly. You must show this highlighted stuff. That plug-in is not negotiable and it can't be simplified. After you write that down, most of you with multifunction calculators can go right to the answer. The ending amount here, $4,118.09. Why do we only need 2 decimal places? That's right, money. Notice in red here, everything's the same, except instead of 4 times a year, we're going to compound daily, which means 365 days a year. And when you do that, you get a whopping, what, 43 cents more than you did if you compounded quarterly. So again, you can put that into your calculator in one shot, but you have to have the highlighted or the red plug-in all written there without simplifying before you get your answers. Okay? This is your homework. Mr. Davis is going to make sure you're on task. Don't bug him. Very intelligent. He can do your homework for you, but he's not there to help you. He's there to make sure you're working. If you have any questions, ask Jane. She will help you. And I will see you tomorrow.